Welcome to Interface. Today we have Professor Rudrajyoti Pallit from Tata Institute of Fundamental Research, Mumbai with us. Welcome to this program.
Thank you, Vinod.
Pallit is one of the active collaborators of the FAIR project in India, and can you tell us briefly about the FAIR project to us?
Yeah. So, FAIR stands for Facility for Antiproton and Ion Research. It's one of the mega science projects in Europe, and it will come online in 2020, and it's a international collaboration between different research institutes and universities across the world. It has one very powerful accelerator which will provide exotic isotopes and antiprotons for basic research. It has 4 science pillars. One is nuclear structure and reactions for astrophysics experiments. This is called Nustar Experiment. The other one is compressed baryonic matter research. The third one is Panda experiments, which is for proton and antiproton research. The fourth one is APPA experiment. It is an experiment to study atomic physics of relativistic atoms and applied physics, and many countries are involved in this mega project.
Okay.
In brief, the project aims to study the nuclear matter and the evolution of the universe.
Okay. What type of exotic nuclei? Can you elaborate on that thing? What type of exotic nuclei you will study with this project?
So, you know, isotopes, there are different type of isotopes can be possible, and one of the a given chemical element can have different type of isotopes depending upon its mass number. Suppose you look for the carbon, which has a major part in a human body, can come in the form of 12 carbon or 14 carbon. 12 carbon has 6 protons and 6 neutrons, while 14 carbon has 6 protons and 8 neutrons. The chemical properties of 12 carbon and 14 carbon are similar, however, their physical properties of 14 are different. Namely, 14 carbon is radioactive and 12 carbon is stable. You know, the 14 carbon is used for dating purposes, and which is used to find out the lifetime of organic material, and 12 carbon is stable. Interestingly, the facility like FAIR can produce heavier carbon isotopes, say 22 carbon or so, where you have 6 protons and you have 16 neutrons. So, it has 10 additional neutrons than the stable isotope, which is 12 carbon. And study of these isotopes are interesting from basic science point of view.
Why these isotopes are interesting for the mankind? What you produce in this FAIR, these isotopes you talked about, how they are important for the mankind.
So, the FAIR facility is a very ambitious project to produce wide variety of isotopes from lighter to heavier elements. Understanding these isotopes is an intellectual challenge, and measurement of the different properties of these exotic isotopes will provide us new insight about the nuclear forces. Some of the isotopes they will play a crucial role in understanding the puzzle of production of elements, chemical elements in the universe. Because these isotopes are expected are believed to be produced in stars during certain astrophysical processes, and their decay properties are essential to know about the elemental abundances. Like in our solar system, we have now hydrogens are getting fused to produce heliums, and as time will pass, the heavier elements up to iron will be produced by fusion reaction. But what happens, or how do you produce heavier elements which are heavier than iron, remains a puzzle, and it is believed that the heavier elements are produced during supernova explosion, which is followed by death of massive stars. So, therefore, the interest in studying this isotope is of basic is interesting from basic research to understand the elemental abundances.
Okay. So, to solve this puzzle, what type of experiments are planned or you propose to study or to solve the puzzle?
See, the experiments, as I told you, that elements heavier than irons, neutron rich isotopes of these elements, they play a role in understanding the abundance of the element in the solar system. Now, you have to measure their decay properties, as well as you have to measure their cross sections, capture cross sections with neutrons, and experimentally you need to produce these isotopes which are short lived and measure their different properties using collision experiments, and then try to understand how these properties they change when you go to more and more heavier neutron rich isotopes.
How do you get to measure these properties?
So, first of all, we need to produce these isotopes in experiment using nuclear reactions involving stable isotopes from the accelerator. Then we need to identify these isotopes. The challenge is that these isotopes, most of the isotopes are very short lived, and during that small time span you need to identify these isotopes. Then we need to do collision experiments or study their decay properties, and in that process we have to measure the light. In case of nucleus, it is the gamma radiations coming from the nucleus, or the other type of radiations like proton or alpha, and neutrons. From there we will be able to study the various properties of these isotopes, and you need sophisticated detection systems and instrumentation to measure the different properties of these isotopes.
Do you expect some surprises?
Yeah, as like any other basic research project, this project is extremely ambitious and has a lot of potential for new discoveries. One of the aspect of the nuclear system is that it is a very complex quantum system, and understanding in detail its structure and the dynamics, what happens inside the nucleus, remains a challenge. The existing effective nuclear forces are not understood completely, and therefore, the state of the art nuclear models have difficulties in explaining very neutron rich or neutron deficient isotopes properties. So, nuclear science is mostly a experimental science, where the experimental measurements they guide the theory, and it improves the predictive power of the nuclear theory. So, one of the aspects of exotic isotopes is that the nucleon force, the effective force, can become simplified when you go to certain very exotic isotopes, and measuring their properties can help in improving certain aspect of the nuclear force. One of the aspect of the surprising research potential of the field is that you can have very different properties, exotic modes of nuclei compared to what you see in case of stable nuclei. One of the example is if you look for an isotope which is stable, say lithium, which is 6 and 7, and then if you keep on adding neutrons to 7 lithium, then you can produce 8 lithium and the heavier lithiums isotopes. And what has been observed, that in case of 11 lithium, which is 4 neutrons more than the stable isotope of 7 lithium, has a size which is that of 208 lead. So, this type of interesting aspect, that suddenly the nucleus can have a very diffuse matter distribution, can give rise to new type of interactions, and you can study the nuclear forces in a medium where the density is much smaller, and that can give rise to sometimes a clustering of nuclei, clustering of nucleons, and it can also give rise to a new form of residual interactions, and that can have a different impact on the other properties of nucleus. We can also study the properties of equation of state of nuclear matter at low density. Then another aspect of low energy nuclear physics with the type of facilities like FAIR will be the study of the magic numbers. We know that nuclei with certain number of neutrons and protons are more bound because of the magic numbers, which is predicted by the cell model. And now what has been observed, that if you see do the measurements for neutron rich isotopes, you find out that these magic numbers change, and though the cell model has been used to explain the properties of nuclei, and it has lot of success stories. Now we are seeing that this aspect, the major aspect of the cell model, which is the magic number, that is also changing when you go for neutron rich nuclei or nuclei away from line of stability. And this type of things will change our basic understanding of nuclear physics. The another aspect which is of interest is to find out the limits of stability of nuclei. Right now we know the limits for isotopes up to oxygen, mainly the neutron drip line and the proton drip line. However, the heavier isotopes, the drip lines are not understood and we do not know, and facilities like FAIR can give us idea about the drip lines, neutron drip line and proton drip line up to Z equal to 25. So, first I should also explain that what is drip line. For neutron drip line is for a given isotope is a limit at which the neutron separation energy becomes 0, and you can have for a given number of proton, you cannot keep on adding the number of neutrons. As you keep on adding the number of neutrons, the binding energy will reduce, and beyond a point the binding energy will become 0, and that defines the limit of stability for the neutron rich isotope. And the FAIR will be able to produce or will be able to help us identifying this drip line for isotopes up to Z equal to 25. Another aspect which is useful for the basic nuclear physics is the super heavy elements. We know that heavier elements beyond mass Z equal to 110 people have produced, but their lifetimes are much smaller, and theoretical models predicts that at a heavier Z around 126 you can have elements which have more stability compared to the intermediate isotopes. So, that is this type of isotopes, if one can produce, will help us understanding the stability of heavy nuclei, and all this type of research will be possible with FAIR.
Yeah, can I ask about Indian contribution to this project?
Yeah, so India is one of the major partner in the development of this FAIR facility, and India groups have contributed in development of crucial components of the accelerators, and the research groups are involved in performing experiments, designing of detectors and testing of these detectors for this facility. There are mainly in two experiments where India is heavily involved. One is Nustar Experiment, the other one is CBM experiment. There are also interest in APPA and PANDA experiments from different groups. Within India, more than 20 institutes and universities are involved in the Nustar experiment in studying the properties of exotic isotopes, and the compressed baryonic experiment, where people will like to measure the properties at high density, and there around again 20 universities and institutes are involved, and they are developing certain detector systems for the CBM experiment.
What about the research group involved, and how many students are involved in India? Or can you tell me more about?
So, as I told you that for Nustar experiments, around 15 universities are involved, and from 15 universities around 25 faculty members and around 25 PhD students are involved in the R&D required for development of the detectors for the Nustar experiments, and planning and simulation of these experiments. To train the students, we recently have organized a school in Calicut University, where we are giving training to the PhD students on the different type of physics which can be performed at fair, as well as the experimental challenges which we need to tackle while doing this experiment, and different type of detectors which will be used or which we are planning to build. We are discussing all these issues in this school, and in this school there are faculties from Indian universities and institutes, and many students are also involved in the R&D projects which is going on in the Indian institutes related with the FAIR project, and some of them also visit FAIR labs to participate in the R&D aspect of the experiment. They also attend the international FAIR schools and also participate in experiments where the testing of the equipment for the Nustar is going on.
So, what are the impacts of this study for the society?
Yeah, actually it's the different type of experimental techniques and the detectors which are used in Nustar experiments, they can be like fine tuned for different applications. One of the applications where the detectors can be used readily is for nuclear imaging. As you know that the detectors which are planned at Nustar experiment, they can find out the position of radioactive sources within half a millimeter resolution. Okay. So, we can use this type of high resolution, high sensitive detectors for finding out the radioactive traces which is injected in the nuclear medicine, and one can do a highly improved imaging capability so that the diagnostic tools sensitivity can be improved. The other application of nuclear techniques is the production of different type of isotopes which are used in nuclear medicine. One can try to see for new variety of isotopes, and then the other techniques of accelerator which is used for in medical science is the heavy ion based therapy for cancer treatment. Also the type of detectors which are used, they can be modified for homeland security purposes.
Thank you very much for to be in this interface. Thank you.
Thanks.